All right. Good afternoon, everybody, and thank you for joining us today. Welcome to the Future of UVEB Advanced Manufacturing, Trends, Strategies, and Applications, a regular webinar series presented by the State University of New York College of Environmental Science and Forestry, SUNY ESF, in collaboration with RadTech International North America, the Association for UV and EB Technology. My name is Brandon Murphy, and I'll be your host today from SUNY ESF. As a quick reminder, all the webinars in this series are archived at the address on the screen, and you'll also receive a link to the address by email after the webinar. You can keep an eye out for announcements from the next webinar from Mickey Fortune with RadTech. And the RadTech 2020 UV and EB Technology Conference is coming right up March 9th through 11th at Disney in Orlando. The conference will feature more than 100 presentations on the latest innovations in UV LEDs, 3D printing and additive manufacturing materials, printing and packaging, industrial coatings, formulations, all sorts of great stuff. There will also be short courses in polymer chemistry, a special UV LED boot camp, and a more in-depth workshop on the design of experiments, today's topic, with our presenter, Dr. Guymon. So you can visit radtech2020.com or to learn more and register, or the RadTech website at radtech.org for more information. And just the registration deadline is next Friday the 21st, so if you haven't registered already and are planning on going, make sure you register real soon. Just some quick logistics on today. We'll have the presentation. Your audio is muted, so we can't hear you. We'll go through the presentation, and then we'll open up a chat window at the end where you can type in questions for our presenter. So today's webinar on the introduction to design of experiments for UV, EB scientists and engineers is being presented by Dr. Allan Guymon of the University of Iowa. Dr. Guymon received his Bachelor of Science degrees in both chemistry and applied mathematics at Weber State University. He then earned both a master's in 1995 and a PhD in 1997 in chemical engineering at the University of Colorado in Boulder, under the supervision of Christopher Bowman. After graduation, he joined the faculty in the Polymer Science Department at the University of Southern Mississippi. In 2002, he joined the Chemical and Biochemical Engineering Department at the University of Iowa and was named the Sharon K. Tinker Professor in 2013. He currently serves as the chair of the Department of Chemical and Biochemical Engineering at Iowa and the co-director of the National Science Foundation Research Experience for undergraduate programs in nanoscience and nanotechnology. He's also the director of the Industry University Cooperative Research Center on Photopolymerization, an industry/university consortium at the University of Iowa and the University of Colorado devoted to advancing the fundamentals and applications of photopolymerization. He's published over 100 articles using UV and visible photocuring in peer-reviewed journals and given over 200 presentations at conferences, universities, corporations throughout the world. He's received several awards, including the 2002 Presidential Early Career Award for Scientists and Engineers. And his research focuses on using photopolymerization to form nano and microstructured materials and on utilizing reaction engineering to engineer specific structures and properties into photocurable thin films. So I want to welcome and thank Dr. Guymon for presenting today.
Great, it's a pleasure to be with you. And first of all, I'd like to thank Brandon, not only for the introduction, but also for enabling all of this, and also with the partnership that enables all of the different webinars. It's great to be part of this, and great to be able to talk to all of you today. In looking at the participant list, I see a lot of familiar names, so hello to all of those who I know. And also look forward to meeting many of the rest of you at RadTech here in a few weeks. And certainly happy to answer any questions as we have time today, and also with follow-up later as there might be interest. So we're going to talk about design of experiments, and it's something that I've been working on for a number of years. Actually, first encountered and started learning about design of experiments when I was in grad school at the University of Colorado, and had the opportunity to use it in my research, as well as develop this and many other courses I'll talk about later with Roger Hester at the University of Southern Mississippi, and have had the opportunity to work with RadTech in doing the webinar, as well as the course at RadTech that we'll talk about at the end for a number of years, which has been a great privilege and a lot of fun along the way. So I will emphasize we have an hour, and design of experiments is not a topic that we can learn everything there is to know about in an hour. So it'll be a primer. Really get an idea. Many of you have probably used design of experiments, have an idea what it is, and refresh on some of the basics, but more provide a motivation of why would you want to learn more, and why could this be useful, especially in the field of UV and E-beam curing. And then we won't be able to talk about too much of exactly how that works with UV and E-beam, but I'll give you some examples, and certainly I think you'll be able to think on your own as we go through this, how might this be useful and be able to be utilized in your work. So just to give you an idea of what we're going to talk about and give you an outline of the next 45 to 50 minutes before we answer questions, is I do want to give you a basic introduction and motivation. So especially for those who haven't used design of experiments, why would you want to use it, what is it, and how could it be useful? And then we'll go into some of the nuts and bolts, talk about how you might put together a design of experiment or designed experiment, basics of designs of experiments, and then talk about the three primary types of designs, screening designs, model building designs, and mixture designs. And we'll go into a little bit of detail so at least you have an idea of how those might be useful in things that you actually do. So first of all, before I get into too much of the introduction, you notice that oftentimes when you see design of experiments, you'll see it called statistical design of experiments. Now on purpose, when we put this type of material together, we don't put statistics, because I think the reason why statistics is put in front of it is because statisticians want you to feel they're very valuable in doing all of this, and they're necessary. They're not. Statistics are important, and they're a valuable tool, and certainly an element of design of experiments that is part of what you have to use, but you don't have to be an expert in statistics by any means to use design of experiments, and there's a lot of software packages that help guide you through the statistics. So emphasizing on the design of experiments, not the statistics, is really what you should be thinking about. How do you effectively design experiments using this technique that is based on statistics, also based on linear algebra, that allows you to get more information with your experiments. And that's what we'll talk about here over the next little bit. So to give you a little bit more of an introduction, so what is design of experiments, or statistical design of experiments, as I mentioned? Okay, so if we think about it, to really define it well, it's a careful and efficient plan for data collection and analysis to test hypotheses. And the overall idea with this, and this is certainly what got me interested when I was in graduate school, is you wanted to get more information with fewer experiments, or how do you maximize the amount of information with fewest experiments? So that's one element, but the careful and efficient plan for data collection is really key. And then the analysis to be able to test hypotheses is the next element. And then, of course, we'd like to do fewer experiments to find that out. So where does this actually come from, and how do we actually use this? Well, so the ideas would be, and I show some potential examples in UV E-beam curing on the right, but perhaps you might want to improve a process. You might have a product that needs improved as well. Another aspect is perhaps there's too much variability in the end results of something you're doing, and how would you lower that product variability by changing some of the variables, some of the processing conditions perhaps, to get a more stable process, which also relates to process robustness. So if there are changes, if the weather changes outside, if something small part changes in your system, that your system can withstand those small perturbations and still give you a reasonable result in the end of properties. And you can also use this to help you understand more about your processes, expand the knowledge, the scientific knowledge of what you're doing. That's not the primary tool. We're certainly not a research tool in many ways. This is much more of an optimization tool where you already understand a lot about the process, but it certainly can point you in directions that you didn't think of beforehand. So with that, let me give you a little bit of the reasons why you might want to use this, and what are the advantages. So one of the primary advantages when we look at design of experiments is the ability to to do many factors, many independent variables in essence at the same time. So mostly what we do as experimenters, as scientists, as engineers, is we vary one factor at a time. We change one variable, fix everything else, and we see how that impacts our ultimate properties, whether it's gloss, whether it's adhesion, whatever it is we're looking at. We're just looking at perhaps the effect of temperature, the effect of initiator concentration, or the effect of oligomer concentration. And we change that, and we try to fix everything else. Design of experiments allows us to change many factors at the same time, and in so doing understand how when you vary multiple factors, really certainly sampling a much greater space of the different factors than you could one factor at a time, where you're just drawing a line through a multidimensional space. Also, you can understand interactions, and I'll talk about what interactions are in just a second. So part of what we want to be able to get out of a design, if we do it appropriately and design it correctly, is we want to be able to not only find what our model is, but we may not know which of those factors are important. There's so many of them, it's hard to deconvolute just one variable or one factor that might be important. So which ones are most important? And of course, which interactions are most important, at least within the experimental error that we can limit ourselves to. We also may want to find, and this is what I think a lot of people want to look for, is which values of particular factors are going to optimize our response. And when we say response, that's our dependent variable, where the factors are independent variables. It might also tell us we're not in the right space yet, but it can tell us what direction we might want to go. Perhaps by changing a few of the variables in a particular direction, we can get a better ultimate result. And then, of course, what we really would like, and very few designs just have one response. We have several responses. How do you find the best overall conditions trying to use responses that usually may not work well together, that as you optimize one, you decrease another. So how do you optimize all of those at the same time? So let me come back to the idea of what an interaction is. And this is something that we do not see at all when we do one factor at a time experiments. Now, that is, if we have two different factors and we change them, we will obtain a different response when the second factor is changed. So they interact. And I think you understand the basics of what an interaction would be, but it's something where it isn't an independent. You can't change one without it changing the effect of another. And that's very important. It's not something that is easily obtained unless you do a very rigorous multivariable, multi-factor experiment, and be able to model it appropriately. And design of experiments enables us to do that in a fairly easy way relative to a lot of other techniques. So let me give you a little bit of background. So where does design of experiments come from? So many of you have probably had the opportunity, or you might not have looked at it as an opportunity to take linear algebra. So linear algebra, if you remember, had a lot of matrices in it. So the basis of linear algebra, and a lot of what we looked at with linear algebra, was developed by a mathematician. This mathematician's name was Jacques Hadamard, and I apologize for those who speak French better than I do. He was a mathematician. And what he figured out is he found that by using matrices, he could develop matrices that were independent. By independent matrices, if you go back to the concepts of linear algebra, they're in essence independent equations, independent linear equations. If they're dependent, then obviously there was issues. I think you might have remembered solving systems of equations, right? And you can use matrices to do that. So that's really based on the work of Jacques Hadamard. And he developed all these independent matrices that could be very interesting. Now, he didn't really have an application for them, but it was very interesting from a mathematical perspective. So along came another very important scientist. His name was Ronald Fisher. And if you take the course at RadTech, I'll actually tell you why his name is Sir Ronald Fisher. But he was a statistician and a geneticist. Did a lot of work in many different areas. But what he figured out was that he could take these independent matrices developed by Hadamard and develop what we now know as multi-level full factorial designs, where you could have, with a set of a number of experiments with a number of factors, you could actually use those matrices to design experiments and to come up with models to describe the results of those experiments. And that's really where the basis of everything came from. And the other thing you might know of with Sir Ronald Fisher is the F test in statistics. That actually also comes from him and is named in honor of Sir Ronald Fisher. So how do we use them? So this is really the key. So now that we know that we could use them, we can vary multiple factors at the same time and get responses based on that. How do we actually do that? So why we want to, the main purpose of any of these, and this is really any of our experiments to some degree, we want to be able to predict what happens in a particular space. So our basic premise is that we can take any data where we vary lots of different factors or even just one factor, and perhaps we can, and the idea is we can model it to some sort of mathematical relationship. A lot of what we do in science, and what I actually just taught about first order, second order reactions today in class, is you want to model it to a line, right? It's really nice if you can break it down to a two-dimensional line. But very few of our processes can we boil it down to one variable that we can, and then put everything on a line, no matter what we do, no matter what transformations we do to it. Usually we need a polynomial, right? And the more complex the polynomial, the more experiments we have to do to try to be able to get enough data points to develop that relationship. So that's the basis. What design of experiments helps us do in relationship to that is it helps us choose the values of our independent variables, our factors, that will help us get the most information we can per point per experiment. So we would like them to be simple, but again, we're not going to always be able to get them to be simple. So we may have to go to second order terms, maybe to third or cubic in some cases, but we want to be able to keep it as simple as possible. That certainly gives us a better opportunity to model our systems accurately. So that's some of the foundations of what will allow us to do experimental design. Okay, so let's talk about the model building itself. So we want to develop this polynomial perhaps where we can estimate it. The other power and value of the design of experiments is we can use these techniques, we can use these matrices to actually calculate the coefficients. Now, is this something you would ever need to do? Absolutely not. This is the foundation. You'll have some sort of software program that will calculate it for you. But at the same time as we can use the techniques to actually find what they are. And that's some of the power. This is not just doing a nonlinear regression. This is actually using the DOE techniques to find the coefficients themselves. So with that, we may want to model something. This is actually a linear expression where we have two independent variables or two factors, x1 and x2. And b0, b1, actually I'll use a pointer here to show you, but b0, b1, b2 are the coefficients that are going to be associated with each of these variables. And we also see this term x1, x2, which is an indication of the interaction between variables 1 and 2. So with that, what we want to be able to do is not only see what the value of these coefficients are, but we may want to use that as a value. So perhaps b1 is much greater than b2. Perhaps b2 is not an important variable in our process. We think it might be, but maybe it's not. So design of experiments and statistics will allow us to determine whether or not this is significant. b2 is actually significant compared to b1 perhaps. And it also will tell us which interactions might be important. It might also tell us if we need squared terms as part of our model. That might not be initially in part of our model. That's all based on the estimates of the magnitude of these coefficients, for example. So the other thing just to mention, and I think this makes sense, it's logical, that we really can't use this model that we're showing here as a way of describing everything that's happening in our process or our system. This is only really valid in the factor space that we've established using our design. So that's important to note. So it can help us predict the direction, but we certainly don't want to rely on that to base a new process. All right, so this is just a very simple, very general list of things. If you're going to do a designed experiment, it's a lot more involved than if you're just doing one factor at a time, where you can just vary it randomly at different points along your independent variable scale and find some results. In this case, you need to know what you're doing when you start. You have to know what experiments you're going to do when you start. It's very hard to change midstream in a design. So it's much more important to do a lot more work at your desk, perhaps, in designing this than in the lab, perhaps. So make sure you know as much as you can about the process before you go forward. You want to make sure that you define your problem statement. And this is important too. A lot of our responses may not be quantitative. It's much harder to model a qualitative model, to actually get a polynomial that describes something that's not quantitative, right? So we want to try to make it as quantitative as possible. We obviously want to know what our objectives are, what do we want to get out of this. And this is where some of the details then. We want to select responses, meaning the dependent variables and the ranges that we might expect in those responses. If we have responses that we can't measure, then that's going to really create havoc in our design. We want to be able to make sure everything's measurable and all of our factors and levels of those factors, meaning the different values of our factors, are reachable. So we don't want to have a temperature that we can't reach. We don't want to have a percent of initiator that won't allow initiation to occur, for example. All of those things are things we need to think about. And then you want to think about what are your resources. So how much time and effort can you use, and how much time and effort does it take to do each experiment? Is one of the mistakes that a lot of people will make is they'll try to do everything at once. They'll try to do a huge design with 256 experiments, right? And then you approach management and you say that I need this many resources to do this, and they say, well, that would take 4 months. Of course you can't do that. At the same time, if you look at this and you take about a third of your resources to put into your first design of experiments by doing a few designs and informing yourself on the next design after the first design, you can get a lot more information with a lot fewer experiments. So at that point, that's when you're going to decide what type of design you're going to use, what type of analysis you're going to use. These are some standard experimental techniques. You're going to randomize things, conduct the experiments. So we've really got to 9 before we've really done any work. Then you do the analysis, and again, software makes this very easy to be able to do this, make conclusions and predictions, and then probably you're going to set up a new design after that. You're going to use this design, probably a screening design, to figure out which variables are most important, which factors are most important, and then use that to find something where you can get more of what we call a model building design that I'll talk about in just a couple of minutes. Okay, so before we go any further, you cannot in any way, and in fact, if you have a very error-prone process, you're also going to have a difficult time getting good information from a design. So it's no different than any other experiment. If you put garbage in, you're going to get garbage out with this. And large error can really make it so it's very hard to get any meaningful conclusions. You might at the end of a process, after spending lots of time, find out from a statistical perspective that the only thing that's important in your process, varying multiple factors, is the overall mean, which is a very undesirable result, what you do. So you certainly want to reduce error as much as possible going into this. And there is a balance because I know that part of this is to try to reproduce what's going to happen when it's actually in the plant or on the line. At the same time, though, if you allow too much error to be introduced, you're not going to see much. And so you want to try to minimize it as much as possible, at least get to the ranges that are going to give you the best opportunity for results in your final process. And this is a standard rule of thumb, and it's not perfect. There's nothing statistical about this. But I'll tell you that at least with the experiments I've worked with and helping companies and working on things on our own, what we've seen is that if you have a relative standard deviation, meaning calculating the standard deviation divided by the mean, if that's greater than about 8%, it's very difficult to get a lot of information from your design. You might get a little bit, but then your signal-to-noise ratio really, it makes it hard to find a lot of information. That's just something to go forward with. It's not going to fix any error you have. In fact, it's going to make it worse and harder to be able to determine good information. All right, so with that, let's talk about something else. So in doing design of experiments, we do a transformation. You know a lot of transformations, you've dealt with them before. If you take the sine of an angle, if you take the exponent of a number, those are different transformations. What we do, what we'll have to do actually to make this work, is we will take a real space variable. Let's use photoinitiator concentration as an example. A real space variable of, say we have 3 levels. Levels are the different values of the factors, from 0.5%, 1%, 1.5%. What we're going to do is we're going to transform this real space variable into a factor space. The lower value we're going to assign a -1. The middle value we're going to assign 0, and the upper level is going to be a +1. Now there's a lot of reasons for doing this, but the main reason is we want to be able to assign over a particular range all of our factors having the same magnitude. So we compare this to, say, photoinitiator and temperature. Perhaps we're changing temperature 60, 80, and 100 degrees Fahrenheit, as an example. You notice in this case, the photoinitiator concentration is only changing 1%. The temperature would change over 40 degrees. And you want to put that into a model. So by transforming this and making the lower level of temperature a -1, as is the lower level of photoinitiator, and the upper level, the top level, a +1, now we're assigning the same range of coded factors to both real variables. So we're no longer, the model doesn't have to adjust to us in terms of trying to understand the coefficients. Magnitude now will be relatively important. So the magnitude of the temperature and photoinitiator will now allow us to compare the importance of factors, and actually allows us to eliminate some that may not be important in the long run. All right, so hopefully you followed so far. We're getting a little bit more into what's going to really happen with designs and more of designs, and hopefully have a little bit more of an idea of why you would do this. So let's actually do something else first. Just for a second, I've thrown a lot of terms at you for the first 20, 25 minutes here. I want to at least give you an idea. If you've heard these before, then you understand things a little bit better. But something I noticed when I started doing design is all of a sudden everything that I knew before, now we're using different terminology for. So I just want to go over a couple of these again, just to make sure you understand. When we talk about a factor is really our independent variable. It's a controllable experimental variable that's thought to influence the response, right? So we don't put a factor in there if we don't think it's going to change our ultimate values, our properties, our whatever it is that we're looking at for a particular process. When we talk about the level of a factor, that's the lower level is -1, upper level is +1 in coded space, but that could be the 0.5, 1, and 1.5% photoinitiator, for example. The response is our dependent variable. By changing the factors, the idea is we're going to change the response. This is our dependent variables that we're actually looking at. And obviously, we can have several of those. We've talked about interactions. When you have joint factor effects, where changing one factor changes how another factor influences the response. Something else that will happen, and then again, we'll get into more detail on this if you take other courses, but confounding means that sometimes, depending on the type of design, you're not going to be able to attribute an effect to a single factor interaction. And we can go into more details on that later. There's also covariates, things we can't control. We'd like to be able to ascribe everything to a factor, but in many cases that's just not possible. And we have to try to understand them, but we really can't control them. So that's certainly something. And if we say something has an effect, that means by changing the factor levels, that we see a meaningful change in the response. That means that particular factor has an effect, is what we would actually say in that case. All right. So with that, let's actually get to do a design. So we're going to do a very simple design and show you how this is done. Again, not anything complex, but at least give you an idea of the ideas that we would use. And I'd suggest if you're doing this on your own, you go through the steps I mentioned earlier. But let's say we're going to do a basic photocuring design. Now, one of the things we're going to want to do is we obviously determine resources, what type of design we're going to use. In this case, I want to just brainstorm, at least I will brainstorm with all of you, of what are some different factors and what are some different responses for a basic photocure. So let's think of some, and there's some that come to mind. We already mentioned initiator concentration. So we also want to look at perhaps the response. What's most important to us, and what are we going to try to optimize? So we'll just use a couple here. So one might be your ultimate conversion. How much is reacted if you're doing an acrylate or methacrylate, the double bonds, for example, of the conversion, or an epoxy, how much of the epoxy rings have actually reacted. You could also look at perhaps the adhesion strength. Maybe you're doing a T-peel adhesion or some other adhesion strength measure. That's maybe your primary goal is improving adhesion between substrates, for example. Just a simple example. And obviously you can go a lot more than that. So in fact, you probably can come up with 10 or 12. Many of the designs I've worked with different companies over the years, we've had upwards of 15 responses depending on the particular system. So then you'd want to say, okay, this is what we want to try to fix. Are these, or we want to try to improve or optimize or achieve a certain level? So what factors and what are ranges of those factors? So I mentioned photoinitiator concentration, right? That's one thing that certainly could affect the conversion and adhesion strength in a particular process. Perhaps maybe we're going to go from the 0.5 to 1.5% that I mentioned earlier. Obviously, it can be any range that's based on what you feel is appropriate. Also, maybe temperature we think is important. Maybe not be, maybe it is. It's an easy one to think about. So in this case, let's go from 60 to 80 degrees Fahrenheit for our particular process. Obviously, we can have a lot of different factors. We can start adding oligomer concentration, right? So at different levels. We can also, maybe from 60 to 80%, this is a high oligomer concentration system. We can obviously put the reactive diluent concentration. We can start talking about the belt speed. We can talk about the light intensity. We can keep adding and adding and adding here. So we don't really have time to go through all of those, but I think you can do that brainstorming which factors are most important. Now, obviously, every factor we add here is going to add the number of experiments, something to keep in mind. So those are all probably pretty important. Now, there might be some other variables that we think are important, but maybe are not. Well, maybe belt speed. Belt speed light dose is probably going to be critical for these. But maybe someone told us at one point that phase of the moon was important, and that we had to vary that. Now, obviously, that seems a little bit silly at this point, but there are a lot of the factors that you have that you think might be important, but you have no way of telling whether they're important because you always do the one factor at a time experiments. And perhaps someone in the past used phase of the moon as one of their one factor time experiments and saw changes in properties. So there has to be a way of identifying whether that's important, especially relative to these other factors that we would probably assume were important in our particular process. So that's just part of the design aspect. So what we're going to do, though, is we're just going to pick a couple of these just to give you an idea of a very, very basic design. And this you could have come up with your own. So let's say we're going to do photoinitiator concentration and just temperature because they're easy to think about. And we're going to do a two-level, two-factor design, right? So about as simple as you can get. So 2 levels, meaning we're going to have values at 0.5 and 1.5% photoinitiator and temperatures of 60 and of 80 degrees in our particular system. So if you think about that, if you have 2 levels, 2 factors, probably most of you can think that's 4 experiments, right? So let's put those experiments together. So we have 4 runs, 2 of them are at the lower levels of photoinitiator, 2 of them at the higher levels of photoinitiator, and of course we're going to alternate temperature between those. Those are our 4 runs. So that's a designed experiment right there. 2 level, 2 factor. Now I mentioned we're going to have to put this in coded space. So let's put this into coded space. So now the lower level of photoinitiator is a -1, the upper level is a +1, etc. And we actually use this for a lot of reasons. It also helps us to be able to find coefficients appropriately and also identify interactions appropriately. So that's the basic design. Okay, and that's very simple. Now let's go into more of other types of designs and give you at least a background of what can you actually use. I mentioned screening designs a little bit earlier. We also talked about model building designs. So screening designs are very powerful and they're very underutilized. Especially statisticians don't love them because you're not reproducing every possible combination of all of your levels and all of your factors. So what this does, and it's a very, very interesting, and everyone I've done has been very insightful in the past, is trying to figure out which of a number of factors are important and being able to determine which of those are important. And it doesn't really help as much in terms of optimization or model building, but it certainly helps us a lot in terms of determining what should we be focusing on if we're doing a model building design, for example. So we don't have to do as many experiments. Also, the model building designs are the designs that I think a lot of people think about, where you're varying factors over multiple levels and you're modeling that to a nonlinear equation of some sort The idea is you're really looking at how that changes over the space of the several factors that you're looking at, and being able to estimate the response as you change those factors and interactions through that system. And another one that's very valuable, especially those who might do more formulations, that we haven't really mentioned yet, is called a mixture design, a simplex or a mixture design. So we've talked about factors as being independent, but you know that if you're going to change the photoinitiator concentration, that by definition you're changing something else, because the composition of your formulation always has to add to 100%, or a fraction of 1. And so this is a way of doing a formulation design where you can vary components and compositions over different levels. It's also a very powerful design, actually, very interesting and very useful in a lot of different scenarios. So let me actually at least give you some very quick and very basic ideas of some of these common designs. So screening designs, and these might be familiar to you, fractional factorial designs, Plackett-Berman designs. You might have heard of Taguchi designs before. In terms of model building designs, and this is not an exhaustive list by any means. Full factorial is, again, what most people feel most comfortable with, but you're doing the most experiments possible. Box banking, which is actually indicated by this design, where you're changing things over multiple levels, but you're not hitting the corners. Central composite, which is one of my favorites. It's actually a very powerful design where you're varying things over multiple levels. And you can also have equiradial designs, where it fits on the points fit on a circle or on a sphere, or even greater dimensions than that if you're interested. And of course, the mixture designs, which is indicated by this triangle plot here for just a simple water urea alcohol mixture, looking at the viscosity of that system, where you actually represent it. This is a ternary plot with 3 components. You have different mixture designs, simplex lattice, simplex centroid, but they both use very similar principles between the two. So let me give you just some brief examples of some of these, and then we'll wrap up and answer questions as we have time at the end. So a screening design. So the whole idea of a screening design is you have a lot of factors, and you want to figure out which ones are most important. Not necessarily saying others aren't important, but especially if we're doing a model building design where we want to vary things over more than 2 or 3, even 3 levels, we need to be able to reduce the number of factors that we're using. So this is a way of determining which of those factors are most important. Oftentimes, and almost always, if you take a full factorial design, it's a subset of a full factorial design. And oftentimes, that's why we call it a fractional factorial, is it's some subset of that. And you always want to use this first if you have a lot of factors. Don't go into response surface design where you have 7 factors. That's tantamount to experimental suicide. I mean, you're just not going to be able to get it done. It's not going to happen. So do this to eliminate some of the variables that you think might be important, but maybe they're not as important as some other variables, right? So always do a screening design first, especially if you have multiple factors. If you're already down to 2 or 3 factors that are important, you can go straight to the model building design. Okay, so you can also get some idea of the interactions, but they're typically confounded, meaning you can't get as much information. So you do sacrifice a little bit. Screening designs mean you're not going to do as many experiments. You're going to take out a significant number of what you would do if you're looking at all combinations. And because of that, you're losing some of the information you would have gotten from a full factorial or a model building design. So, and we understand that going into it. We understand we're not going to get as much information. The primary focus is finding which of the factors are most important, but we might get a little bit more information beyond that. So some examples, fractional factorial Plackett-Berman. Here's a Plackett-Berman 8-run matrix where you can actually look at 7 different factors and try to determine which of those 7 factors are important. The plus would be the higher level, the minus would be the lower level of each of those 7 factors, just to give you an example of that. All right, so full factorial design. This is the first of a model building design. Okay, so these are easy to think about, right? So you have K factors, you have L levels. So this is where you're using every possible combination of every factor in every level. So the total test conditions is L to the Kth power. So if you have 3 factors and 3 levels, 3 to the third, 27 experiments. If you decide to do 4 levels, then it's 4 to the third power, and you can kind of start doing the math of how fast the number of experiments are going to increase as you increase levels or increase factors. It goes up much higher than you probably will want to do for your experiments. The advantage is there's no confounding of factors. You know, we can look at all of the coefficients independently, and this is actually the basis of what Hadamard developed, or the full factorial designs. And you can use two-level full factorial designs. That is also more of a screening design, but you can get more information about the interactions. But if you're doing more than two levels, that's where you can look at a few important factors and develop response models. But this is the big disadvantage. It's easiest to execute, it's easiest to understand, but you're going to do the most experiments you can possibly do with a full factorial design. So what's the alternative? There's actually a few different alternatives. Here's a central composite design where you actually you can do it sequentially, or you can do it all at once. In this case, for a central composite design, you actually change each of your factors over 5 levels. And you see the values here of minus 1.668. Again, that's all relative to our linear transformation to coded space. So again, I can give you more details about that later if you're interested. But the idea here is you can actually do it sequentially, where you can do a 2-level factorial to see if that actually fits your data sufficiently. If it doesn't, you can add the axial points that you see here, 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 and here, et cetera, for the 6 different faces of the cube. You have some center points that you're actually going to add in there. And what I'll say here is with this, the idea with this is 3 levels. You can have 9 center conditions, 6 axial conditions, 8 factorial conditions. So you look at that, it's 23 experiments. And this is varying all of your factors over 5 levels. This is fewer experiments, and in my opinion, you get better information than a full factorial design that you would have used the same thing, which you would have had to do 27 experiments. And you would only have 3 levels if you did 27 experiments, just to give you an idea with that. Okay, so moving on. So just another fun one that I like a lot is Equiradial Design, especially hexagonal design, and if you're looking at 2 factors. And one of the reasons why you might want to use this is because one of your factors is a little bit trickier to model than another. So in this case, you're actually going to vary one of your factors over 5 levels, and the other one you're going to vary over 3 levels. And with 12 experiments, you can get quite a bit of really nice information. Now you notice that there are a lot of center points. There's a few reasons for that. One is to reproduce the real error for your system, and another one is to try to make things as independent as possible using the matrices that we would use to be able to show and be able to determine the coefficients. Again, not something you have to worry about, but this is what the program is actually going to tell you as how many center points you need to run. You really have to run that many? That's up to you. All right, so let's go on to mixture designs, which again might be more interesting to a lot of you. If you do any formulations, this is a very powerful design. Again, the component must always sum to the same amount. Now, it doesn't always have to sum to 1. You can have a base formulation that might be 85%, and you're only varying the 15%, but you have to be able to vary the different components over that amount that you're actually changing. And there's some different ways of working that out that I'm more than happy to talk to you offline. The idea is that you have to sum to the same amount at any point. And your fitting points on this triangle that you'll actually use to model the whatever you're looking at for a particular system. So you can do 3 components. Those are pretty easy to show on an equilateral triangle or ternary plot. If you do 4 components, we've actually built a model of this where you can actually do it on a tetrahedron. One thing that this is where it really comes in value, if you think about this, is if you use a cubic model for 3 components, the minimum number of experiments you need to run is 10. Not very many, right? So now you're varying all 3 components. You're not just trying to vary one and try to keep things constant, which you really can't in a mixture design. You can also go to 4 components, and you only need 14 experiments. Now, you usually will add a few more than that to access more of your error and be able to do some confirmation points, but that's the minimum you would actually need to be able to come up with a design. And they work. I'm just going to tell you, everything I've done, it's amazing what you can come up with just that number of experiments. All right, so we're wrapping up here. We're getting close to the time where I said we're going to answer questions. I want to at least show you a result of one mixture design. This was actually this is from real data, where you're changing 3 different monomers or oligomers in a particular composition, and you're looking at the coating viscosity. as a function of these three variables. And I won't go through and try to show you exactly what's happening in this plot, but I do want to identify that you actually see from just these 10 experiments, you can identify a maximum viscosity, you can identify a minimum viscosity, and a lot of viscosities in between, which you could use to optimize some particular process where maybe you need a higher viscosity, maybe you need a lower viscosity depending on your system. That certainly leads to the ultimate properties of a coating, a UV curable system, for example. All right, so the other thing just to mention briefly is response surface analysis. So one thing that you're going to want to do, once you have this model from a model building design or even with a mixture design, is you want to be able to optimize. You want to be able to figure out where the best points are to be able to run your process or the best formulation to use. This is going to be done by your software. This is not something that you're going to have to figure out how to do. At the same time, you need to be able to understand what it uses. And it uses what's called a response surface analysis. It's just basically figuring out where the highest point on the mountain is. If you're a hiker, that's really what you're doing. And you can put in multiple conditions of what you're trying to optimize, and it will do that for you. So the programs, and there are a lot of programs out there. I'm certainly not endorsing anything. When we teach the course, we usually use Design Expert because it's usually the most user-friendly, and it is focused on design of experiments, but there are a lot of others. Minitab is also extensively used and is pretty good. I don't like it quite as much as Design Expert, but that's just because that's what I learned on first, and it's easier for me to use. But I have used Minitab multiple times. A lot of other statistics packages, not just JMP, but many others also have design of experiments add-ins. They're usually not quite as flexible as Design Expert or Minitab, but there's certainly things you could actually use. And the software is what's going to produce the graphs, what's going to do the analysis for you, do everything else you need. All of the other math I mentioned to you today is you don't have to do. The statistics you don't have to do. You just have to be able to use the software. And by using the software, it will give you a lot of the information that you want. All right, so with that, just to summarize, hopefully in the last 45 minutes or so, you've been convinced that this could be a valuable tool. Those who've already used it probably know that, and you can talk to other people who've used design of experiments, and they can help you a lot in understanding how you could use that. But the idea is to minimize the number of experiments while getting the maximum amount of information. And of course, finding out interactions, which you cannot do with one factor at a time experiments, which is impossible. So I will also tell you, I mentioned a lot of different designs. They all use the same process of determining what's important, which coefficients are important, using basic statistics to do that. They generate graphs. You can look at the coefficients. You can model them. All of them use the same principles. Even though they look different, all the principles are basically the same through all of these. And so the one bit of advice I would give, especially for those who might have used this more, is start with a screening design. Do a model building design where you use a little bit more resources and you limit it to 2 to 3, maybe 4 factors. And then, of course, you're going to want to confirm things at the end to make sure everything that you've done is appropriate and makes sense from what you're trying to do. So I alluded to this, and Brandon mentioned this at the beginning. So this is really just a basis. We talked about this for 45 minutes. If you want more information or you think this might be valuable, and if you're going to be at RadTech, I will be doing a little bit longer example of this where we're going to go through more specific designs. We're going to talk about the screening. We're going to talk about the model building. We're going to talk about the formulation designs. And we've done it hopefully where it doesn't really conflict much with what else you're doing. So it's on Monday evening, and then also Tuesday midday. And actually lunch is brought in on Tuesday, so you don't miss lunch. But this gives you an opportunity to get in a little bit more detail to see if this is something that could be useful to you. So we are going to talk about a lot of things. We'll actually show a little bit of Design Expert if you're interested in that. There will be a lab that you get to do where you'll actually do a mixture design, and we'll do that in class on Tuesday. So if you're interested, feel free to register. Be happy to and look forward to seeing you there if that's something you're interested in. And then if there are those, and don't do this, this isn't my job, obviously I'm a professor, but we do teach a course. This is usually a 2-day in-house short course. Roger Hester, as I mentioned at the beginning, helped me we helped develop this together a number of years ago, and we've done this at a number of companies, UV Curing and otherwise. We usually do at most 2 of these a year, usually focus on about 1. But the idea is if you really want to develop a design of experiments culture in your company, it's best to have some sort of course. And if it's not something you already do internally, that's something that I'm happy to help do and arrange as appropriate, if that's something that you think might be useful for your company. So with that, thank you for your attention. More than happy to try to answer questions over the next 10, 15, 20 minutes, depending on how long we have before we have to get cut off.
All right. Thank you very much for all of that, Allan. So if you want to type in your questions for Dr. Guymon, he'll answer them as they start to come in. And just another reminder that RadTech 2020, March 9th through 11th, but remember registration deadline is Friday the 21st. So if you haven't signed up and you would like to go, make sure you sign up.
All right. So there's first a question. Are there any free packages that you could recommend? No. It is simple math. And actually, I will tell you that when we developed the course, we did it with MathCAD. So we didn't use any specific package. We did all the math ourselves. So you can do this using a standard math package like MathCAD, Mathematica, but those are also not free. It really is difficult. I was just going to tell you that it is very hard to find a package I would recommend that's free. There are some that does do the basics, but free is relative. Now, I will tell you this, is the vast majority of these packages will give you a trial version that is 30 days, 60 days, where you can try it out for that period of time before they make you pay to use it. All right. So second question, so from someone I know well. So the question is it appropriate to assign a numerical value to a binary response to create a quantitative predictive model? So if you have pass and fail, that's a great question, and you can do that. I think it's better if you can come with some scale of passing and failing instead of it just fails or it just passes. If there's a way of some way of doing a 1 to 5 scale or a 1 to 10 scale, even if you can't get something numerical, being able to put some value that's not just a 0, 1, a binary, will give you much better information in your design. And I haven't come across a whole lot of processes where you can't do at least some qualitative measurement beyond just pass and fail. So hopefully that answers that question. All right, so another question. All right, so sweet spot results sometimes deviate quite a bit from the predictions. Is this caused by test errors? If it is, how could we find out? That's a great question. And obviously you model something and then you think you've done a great job and all of a sudden it's different. It certainly can be the test errors, and it also can be how well your model fits the data, right? You're always going to have this issue with any data you run. This isn't unique to design by any means, but certainly measurement errors are going to influence your processes a lot. So that's why you want to minimize them as much as possible in going forward. So that probably doesn't answer your perfectly, but there are ways of putting your design together to try to figure it out. But that's one reason why you want to use a lot of predictive. You want to do some test points and figure out how well your model fits that. So, all right. All right. I like this. Okay, that was good. So the question is, can you recommend any courses in Design Expert, either online or offered in person? So Design Expert does, and actually a lot of these packages do have courses where you can sign up and you can pay a lot of money and they will teach you how to put popcorn in a microwave at different times. I do like, and I guess I'm a little bit prejudiced here, I think that the course that we offer is a little bit more practical. It's taught more on a science perspective rather than just here's a package and you're baking brownies or whatever else. It's really trying to think of things more as you might as a scientist. So I think that, again, the course at RadTech would be a great additional motivation and give you a bit more information to go forward. And of course, we use Design Expert in our courses just as an example. We don't endorse it. We don't get money from Design Expert. But we do at least give enough information where people can use it after we're done in the courses. So that's really up to you. But definitely Design Expert does have courses that they offer. So that was another question. All right, so let's see. So I'll just read the next question. It says production versus lab/research. Ignore process/production for a minute. How do you in your research manage or handle data that could be nonlinear, non-normal, not in control output? That is a really good question. So I will also say that design of experiments is not the optimal research tool, right? So research means you're discovering, you're trying to find out new things. We have been able to use it when we understand a process relatively well, and we want to be able to find if there's directions or paths by looking at multiple variables at the same time that we wouldn't have been able to see just by looking at specific points. And so, so we actually would typically have something that's nonlinear. I mean, most of our processes are not linear. It would be nice if they were, and if we can make them linear, that's great, but we always can't control that. So typically that's part of what you put in the design, right? Now, if it's not in the control output, if that means that you can't measure it, if it's a complete failure and you can't get a measurement, those are bad in a design. Those are things that are very hard to deal with. You can assign it a 0 value or something that's beyond, but that's tricky. That's tricky. So non-normal, nonlinear is something you actually do. Typically, if it isn't in the control output, meaning that you don't get a value, that's hard. And you really want to stay in the range of things where you know you're going to get responses, if at all possible. All right, so, okay, so this is a really good question. What is the value of repeats and randomization of runs? Both of them are very important. So randomization of runs is really so you're not introducing bias in your experiments by, let's say, doing all of the low temperatures in the morning and all the high temperatures in the afternoon, because you don't change those up. Is what you're doing then is you can introduce unconscious bias into your experiments. You can actually ascribe an effect to temperature that really isn't there. And so randomization is critical. Now, you have to be practical as well. Maybe you're using different nozzles to spray your coating, and you can't just swap out randomly between 2 or 3 different nozzles. And maybe you have to do nozzle 1 and nozzle 2. That comes to another aspect of called blocking, and using blocking factors. That is a little bit more advanced, but it's something you certainly can do where you'd probably do all of your experiments using nozzle 1, all using nozzle 2. So maybe a little bit beyond that. Of course, repeats are important because you're going to get much better values because you're going to reduce, you're going to have points that are much closer to what the real point is and that's going to reduce your error and increase the amount of information you get. That depends on the experiment, how many times you can actually repeat them. And that's really going to be much more of what your resources would allow. Okay, so a couple more questions here. So do you recommend performing a measurement system analysis and or linearity bias prior to starting on DE? I will, prior to starting on DOE. So with that, anything you can do to reduce your error. If you want to do measurements, if there's a way of determining how much error you have in the basic measurement, very valuable. Because you certainly want to be your signal-to-noise ratio needs to be significant. And then if you can do anything in terms of trying to figure out linearity or bias prior, any information you have before you go into the design is going to help you tremendously. Any way you can incorporate, if there is a way of linearizing it. So a great example, again, just talked about this in class today, is if it's a first-order reaction, you can plot the log of concentration as a function, or the log of concentration is a function of time, and that's going to be linear, right? So if you're looking at a kinetic response, instead of looking concentration as a function of time, look at the log of concentration as a function of time. And that's a way of introducing more linearity for transforming data. And that's something we talk about a lot more in the course. So all of those are great. Anything you can do to inform your design will always make it better. All right, so question, could you please share more details about what will be covered in the short course at Radtech? I would just say just come and you'll find out. Register for it. So the question is, if it continues, I'm using Minitab and Jump and the instructor uses Design Expert, would that cause a problem? No. The reason why is because it is just a program. All the programs do the same thing. It's just the format and the interface is slightly different. I have used all of those. I've used Minitab, I've used Jump, I've used Design Expert. And by understanding Design Expert, I can use Jump and Minitab pretty well. And I run into limitations with all three programs, but it is basically the same. And if you bring that, if you come to RadTech, I'm more than happy to you can incorporate these examples just as easily into Minitab or to JMP. In fact, I have a number of the examples we'll use in Minitab already. I'd be happy to share with you. I'm not a big fan of using JMP for design of experiments because it's quite limited, just letting you know, but it is still something you can actually use. Now, in terms of the details, what will be covered, we're going to go into a lot more direct information. We're going to show examples of several designs using coding data. Not necessarily all UV coding, but we'll also throw in a couple of examples of things we've done in my lab in terms of basic designs to show what we were able to find in terms of one of them is an additive manufacturing, and others is dealing with some hybrid systems of epoxy and acrylates, just to show you some ideas, some of the things you can actually get from experimental design that you might not be able to get just by doing simple one-factor time experiments. So really a lot more detail. Obviously a formulation lab we'll do, as well as hopefully giving you a much sounder basis to go back and do some of these on your own. All right, good questions. I even got through all of them and it's 2:01. So any other questions?
Looks like we got through most of them. So thank you so much again, Allan, for presenting on this. Thank you, everybody, for tuning in today. You will get an email after this regarding the link to the archives for all the RadTech webinars. It'll probably be a couple of days before the link gets posted up there. It takes a little bit longer these days to get our website updated at the college. But thank you, everybody. Thank you, Dr. Guymon. Hopefully a lot of you will be at RadTech 2020, and there'll be a lot of opportunities to learn from others and to have conversations in between and afterwards to really get into the weeds on a lot of these things too.
Great. Thanks everyone for participating, and actually again look forward to seeing many of you at RadTech. Those I know and those who I don't. It'll be and actually feel free to pull me aside with any other questions while we're there.